그럼 또 시작을 하겠습니다. 약간 늦게 시작을 했는데 죄송합니다. 자, 오늘 워크숍에 안 가고 남아서 와 있는 게 이제 잘하는 건지 못하는 건지 모르겠는데 해가지고 강의를 들으러 와서 감사합니다. 시작을 또 하겠습니다. Okay, before we begin, before we begin, if you have any questions, then please ask me. So this is probably the only opportunity you can ask about experiment 6. Any questions about the experiments that we did this week?
About how long is this film?
Today's lecture?
No, the experiment. Next week?
Yeah. The same, maybe. It depends always. Probably more difficult than this week's experiment. Just take a moment, please. Any other questions? Yeah, it might take longer, but if you prepare more, you can shorten the amount of time that you have to spend on the lab. Okay? The pre-lab is actually more important than this week. Okay? So the experiment 7 requires you to do something in the pre-lab report, and we'll see. Okay. So again, this is EE305, and the next week is going to be experiment 7, and this is a part of actually the second part of LED-based free space communication. Again, my name is Kyung-Shik Yu, and the next week's TA, we have different TAs, and his name is Kwon-Duk, and he's actually here. Okay, yeah, he's over here. So if you have any questions, then you can send him an email. I learned that many of you actually switched your experiment day from Monday to Wednesday, or from Tuesday to Thursday, something like that. But I don't recommend such a thing, because our TAs plan ahead, so we know the distribution between the days. So we actually plan ahead. But if you do the change of your session at the last minute, then our plan is kind of messed. So it's better for you to keep your original date. Okay, so let me begin our explanation. Okay, so we are doing this thing, the energy-based free space communication. And this week you finished this part, the first week, light source and the photon detector. So I believe that you now understood the basics of diodes and the light emitting diode, and something about the photodetector. Actually, we use the phototransistor instead of a photodiode, but that can be categorized as a photodetector as well. Okay, so we have finished this part, the first week, but in the next week we will make it a little larger. Okay, so in addition to light source and a photodetector, we are going to add a board, computer board, and active filter. Okay, so that's the second week. So what do we mean by adding the boards? So the main goal, or the final goal for the next week's experiment is going to build this kind of circuitry. Okay, so we start from the Atmega 128. I'm sure you have learned about this thing a little bit, and you are going to add LEDs, red light sources, and by modulating the signal, output signal from this Atmega board, you can turn the light on and off. Okay, so if you put high voltage, then there will be a current, and if there is a current, then there will be a light emission from light emitting diodes, and by changing the output voltage, high and low, on and off, you can change the light emission at a given time. And because there are more than one port from this Atmega board, you can actually drive two different signals at the same time. You can connect two LEDs and then turn them on and off independently. And so that will be the right emission part, and we call it transmitter. Transmitter side. It generates the signal and transmits and emits the light. On the other hand, on the right side, we have a receiver, photo receiver, and it of course has some photo detector. We are going to use the same detector, same photo transistor that you used in the first week. And depending on the amount of light, there will be a photo current. Okay? If there's a large amount of light, then there will be more current. And if there's no light, then there will be no current. And if there's a current, then there will be some output voltage, and you can measure whether there's a light or not by measuring the output voltage. So that's the second week, which is next week. And in the final week, week 3, we will send the information. Of course, we start from the usual text and then encode it, and then transmit it through this LEDs and the photo detector, and then you finally decode the signal. That's the topic for the week. So for now, let's focus on this part, the second week, the next week. So what do we do? I mean, why do we do this kind of experiment? So let me try to motivate you a little bit more. So I'm not sure whether you have heard of Li-Fi before. Li-Fi. 들어봤어요? Li-Fi? Wi-Fi라죠. Wi-Fi, right? It's a wireless. But what is Li-Fi? Li-Fi is kind of new research projects, and they want to make a light as a communication channel. So we have illumination light in the room, and if this light flickers faster than maybe 30 Hertz or 60 Hertz, then we cannot notice it, right? So if we turn the light on and off very fast, maybe 1 kilohertz or even higher, then we can send the information. We can maybe use that frequency as an information channel. So in that case, every illumination light or light bulb can act as a some high-speed communication channel. Okay, and it's actually quite interesting. So if you want to find out more, then I strongly recommend you watch this video. Okay? There's a YouTube video. Okay? This is actually one of the TED Talk, and if you click that, then you will hear about the Li-Fi for maybe 20 minutes. Okay, so this kind of the light communication or light-based free space communication is quite interesting. And if you finish this 3-week-long experiment, then you maybe you might be able to understand what's going on under this technology. Okay, so let's go a little bit deeper to next week's experiment. So I talked about the optical transmitter, okay, on the left side, and then optical receiver on the right side. Okay, so this generates generates a signal and modulate the light. If light is on, then we can say it is D-star 1, and if light is off, then it means D-star 0. And by detecting the light signal, light intensity at the photo detector, we know that whether it is on or off. So that's basic scheme. So your goal for the next week is to build the whole thing and check whether everything works or not. Okay, so let's go one by one. Okay, so we start from the transmitter today and end up at the optical receiver. So we start from the optical transmitter. So in a very, in the simplest form, your optical transmitter can be represented like this. Okay? So we have a LED, and if there's some voltage, maybe plus 5 volts, then there will be a current. course, there's also current to the capacitor, and there's current to the LED. And if there's a current, then either emitter light. Okay? So please remember what you learned last week. Okay? Maybe a few weeks ago in my lecture. Okay? So when there's current, then there is a recombination, electron hole recombination. We are supplying current to the PN junction, and when electron is supplied, it will be recombined with the holes, and thereby it generates a photon. Okay? And photon means the light emission. Okay? So if we have larger current, then there will be more electrons per second, and there will be more photons going from this LED. So there are some simple questions. What happens when the digital signal output is 5 volts? Okay, and if this is 5 volts, then there will be current, and current will be the source for the photons. And I'm not sure whether you noticed that or not, but the LED's output light intensity is proportional to the current, because the number of electrons supplied to the PN junction is proportional to the current, and the number of electrons supplied to the PN junction will be proportional to the amount of photons. Okay, so they are all proportional to each other. It's very important not to confuse with the power. The power is a V times I, and the light intensity is not proportional to V times I, but it's just proportional to I. Okay? So sometimes you may think the output light might be, or light intensity might be proportional to the power consumption, but it's not the case here. It's proportional to the current. If you want to find out more, then our department offers many courses on optoelectronics, and I'm actually one of the researchers who are working on the optoelectronics. And if you want to find out more, then you can take the courses next year. Okay, so this is too simple, I guess. You're brilliant, and if your job is just to do this, then you take only a few hours. So we make it more complicated. So you have to make two outputs, and you have two independent outputs from the board, from the Altmetal board, and we want you to make one signal at higher frequency than the other. Okay? So this has a periodic signal on and off, 5 volts and 0 volts. Periodic, it varies periodically. But the period of this signal is smaller, much smaller than the period of this signal, the low frequency. It also flickers. It goes on and off, but it changes more slowly. But this is faster. You have to choose your frequency wisely, and it must be based on your characterization results that you did this week. So you characterize, you measure the bandwidth. Okay, you measure the bandwidth this week. The bandwidth of your LED or phototransistor, and we just said it's a high frequency, and we didn't really say what frequency it is exactly. So you have to choose. You have to choose your own frequency, depending on your experimental results this week. But you need to generate at least two frequencies. Okay, one high frequency and one low frequency. So yeah. So again, this LED generates. It's a type of I would change it. Sorry about that. because it's driven by high frequency signal, this LED generates a higher frequency signal, and the lower LED, this LED, the red LED, generates low frequency signal with a longer period. So we already talked about the basics of light emitting diode last week. So in the previous lecture, so I'm not going to spend that much time here. So yeah, so this is basically just description of what I explained before. If the board output is high, then there will be currents, and depending on that current, or because of that current, there will be a light from the LED. If the board output is 0, then there will be no light. And by controlling the output signal, digital output, you can turn on or off the LED. If you really want to modulate, if you really want to send the information to LED, then your signal shouldn't be periodic. But for our next week's experiments, you are going to generate a periodic signal, just a periodic signal, and then try to turn on and off, try to turn the LED on and off periodically. So to be able to do that, you should understand how to generate a periodic signal from digital board. That's mega 128, and this is the hint. So if you look at the manual of Mega 128, you can notice that there's a main clock in the board at Mega 128, and you can use this signal, clock signal, to make a pulse train. So let's say this is our main clock for the board. Usually it's faster. I forgot. It's a 32 something kilohertz. It's faster. And you cannot control this clock signal, main clock signal. It's fixed. It's the design of the board. You cannot change the main clock. But luckily, they provide additional means to generate the various frequencies at the output port using prescaler, encounter, and combination of them. So that's one of the main tasks you have to do for your pre-lab report. You have to. So I'm going to give you some explanation, but this is not probably a complete explanation. So you have to go home and think about how to generate different frequencies using this main clock. Okay. So the first hint is the prescaler. There's a component called the prescaler in the board, and the prescaler scales the clock signal into half or 1/4 or 1/8. So its frequency, the output from the prescaler will have smaller frequency than the main clock signal. So did you learn this kind of thing before? Or what about this? Did you learn prescaler before in your calculator? 안 배웠어요? 이런 거랑 관련된 수업을 듣긴 했어요. 안 들었어요? 계산기에서는 뭘 했어요? 계산기. 이 전 시간에 이제 계산기 했잖아요.
계산기에서는 그냥 코딩만.
네, 여기서도 이제 코딩에 기반을 해서.
프리스케일러 같은 거랑 뭐 그냥 스택 해가지고 계산하는 것만.
C코드
여기서도 이제 코드를 짜는 겁니다. 근데 그게 좀 어려울 수도 있고. 하여간
교수님, 근데 저기 플락이 이렇게 반으로 잘려서 나와요? 저렇게 잠깐만 봤어요? 잠깐만 나와요?
이 밑에 나오고요.
네.
밑에 나오고 이렇게 나옵니다. UT가 낮죠.
그러니까 하이랑 로우 레벨이 시간이 안 똑같고
안 똑같아요. 근데 이게 다가 아니에요. 그러니까 이게 중요하지 않습니다. 그러니까 그 중요한데 그러니까 이게 여러분이 사용할 최종적인 게 아니에요. Okay, so then if you haven't heard about this kind of thing before, then you probably have to spend some time to figure out what this all about. Okay, and this might take some time, but as I mentioned, if you complete the pre-report, actually the pre-report requires to write a code. So if you finish your pre-report, then it will take a much shorter time in the lab, in the lab session. So anyway, this is the hint. So let's make some more. Let's be careful here. So this is the main clock that I mentioned. So this is the main clock. This is 32 something kilohertz. This is this thing. So there is nothing we can do about it. So it will be fixed from the board. Okay, and what is this? This thing. Ever learned this thing before? 뭐예요, 저게? 멀티플렉서네요. 멀티플렉서는 다 배워요? 이미 배웠어요? Okay, so this is a multiplexer, right? So what's the function? Anyone? 어떻게 돼요?
네?
어떻게 돼요? 뭘 하는 거예요? 뭐 하는 거 같아요? 안 배웠어도 그냥 그림만 봐도 이제 잘 그렇게 해놓지. 여기 멀티플렉스가 두 개가 있죠.
네.
뭐 하는 거야? 두 개가 들어가서 이제 세 개라고 할 수 있는데 뭐가 들어가서 인풋이고 아웃풋이 있죠, 그렇죠?
중에 뭘 받을 건지.
네, 맞습니다. Okay, so this multiplexer selects input and relates to the output. So if this is 0, then it selects this one. If it is 1, then it selects this one. So it connects to here. Or to be more precise, depending on this signal, depending on this selected signal, the output is basically a copy of this one or this one. So basically selects. So okay, so you may select this one or this one. Okay, anyway, the output of this multiplexer goes to the prescaler. And the prescaler prescales the input signal. Prescales the input signal. So the output of at this port, this is this has the frequency 1/8 frequency of the input signal. 1/8 frequency. It's like this. Okay. So if the input to the prescaler is something like this, then output at this pin, output at the 1/8, it's denoted like this. The output will be something like this, and the frequency is basically 1/8 of the input signal. So that's the output here. But output here will be 1/32. The frequency of this signal will be 1/32 of the input signal, and so forth. So even if, let's say, your input signal to the prescaler is 1 kilohertz, then this will be 1000 divided by 8. The frequency of this signal will be 1000 divided by 8. If the frequency of this signal is 1024 hertz, then the output at this port will be 1 hertz. Okay, it's relatively simple. So this scales the frequency. The prescaler scales the frequency of the input signal. Okay, so you have many signals here, bunch of signals with different frequencies. And what's the function of this final multiplexer? This is a multiplexer again, right? So this is the same, but rotated by 90 degrees. So there are 1, 2, 3, 4, 5, 6, 7, 8. There are 8 inputs to this multiplexer. And this multiplexer selects one input and relates that input to the output. Okay. So these three the selections ports must choose one input port and relate that into the output port. So you may get, if this is 0, 0, 0, then you may select, it will select the first one, and if it is 0, 0, 1, then it will select the first one and so forth. Okay? So there will be 8 combinations, 8 possible combinations, because it's pretty previous. Okay? So you can select any of these, any one of these, and then and so far so good, right? So the clock is coming in, and then you can, change it changes frequency. Okay, 1 over something number. It can be 1 over 8, 1 over 16, 1 over 8, 1 over 32, 1 over 64, and so forth. There are many combinations. And the output from this multiplexer goes to timer or timer counter. How about timer counter? Did you hear about it? Have you ever heard of it before? 저 타이머 카운터는 배웠어요? 배웠어요? 그건 나와요? 계산기에 나와요? 그것도 안 나와요? 타이머 카운터는 뭘 하는 것 같아요? 카운터는 뭐예요? 네? 세는 거죠, 그렇죠? 세고 있다가 예를 들어 8까지 쉬어라. 그러면 8까지 쉰 다음에 이제 8이 됐으면 그 신호를 내보내 주는 거죠. 그러니까 펄스가 이제 쭉 들어오는 걸 이제 쉬고 있다가 세고 있다가 8까지 세면 이제 8까지 왔습니다 하고 딱 해줍니다. 그리고 10까지 쉬어라. 그럼 이제 열을 펄스가 이제 10번 오는 거를 세고 있다가 이제 10번 오면 이제 다 셌습니다. Okay, so let me explain this again. Okay, the output of this multiplexer is connected to the timer or counter of this board. You can find more details in the manual. But the manual is like 600 pages, so it will take you cannot read everything, but you have to look for the correct information. So anyway, this goes to the counter or timer. Sometimes it's called timer, sometimes it's called counter because they are essentially the same thing. If you can count the number of pulses, but if you can count the number of pulses, then you can measure the time because its frequency is kind of fixed. So the timer and counter, they are actually the same. And the function of counter is basically to count the number of pulses. Okay? So as I mentioned before, the duty cycle is actually not very important because you just count the number of high pulses. So the duty ratio is actually not important. So if you set the counter to count maybe 10 pulses, then it either watch whether the pulse either wait until it receives 10 pulses, and then it toggles the output. So so by changing those numbers, by changing those the counting numbers, you can change the output signal. So the input to the frequency of the input to the counter. Let's say that's 1 kilohertz, and you say to the counter that you have to count 10. Then either signal us every 10 pulses. Okay, so the output from the counter will be 100 hertz. Right? Because 1000 hertz pulse is coming in, and it will signal us at every 10 pulses, which is 100 hertz. So you can generate a 100 hertz signal. And by setting this counter, you can generate many different frequencies, right? Yeah, you can generate many different frequencies. So you have to choose right combination of this selector and then the counter. And by changing those numbers, you can generate some output signals with arbitrary frequencies. Any question up to now? 있어요? 질문 있어요? No? So it will take some time if you're completely novice about this kind of thing. So anyway, that was about transmitter. Okay, so we talked about how to generate digital pulses, actually periodic digital pulses, and when you generate the digital pulses with a higher frequency and a lower frequency, then you can make the LEDs flicker at the different frequencies. Right? And now your job is to detect that signal. So it's relatively simple, simpler than the transmitter side. So you have, let's say we have a phototransistor. The diagram is a diode, but let's say that it's a transistor. And if there's a photocurrent, then there will be a voltage drop between here and there. So you can measure the output when there's a current, photocurrent. And but if you think our transmitter, there are two signals, a high frequency signal and a low frequency signal. There are two signals simultaneously coming to this photo detector, and your job is actually to discriminate or to pass only the high frequency signal. So let's say you generate 1 kilohertz signal at the high frequency LED, and maybe 10 hertz signal at the low frequency LED, and you delete all those low frequency signals, and you want to only receive high frequency signal. And that's your final goal for the next week. Okay, so optical receiver is actually being used in many applications, not just for Wi-Fi, but it's actually it's a motor. Sounds strange, but in the motor, you sometimes want to measure the amount of the revolution frequencies, how fast it rotates. And the one way is to make a wheel, like a fan, and of course the fan is a black mark, and you shoot the light, and depending on the number of rotations, you can measure the output at the receiver, and so forth. There are many other applications of optical receiver. But what's important is that the optical receiver tries to measure the light intensity instant on the photodetector, and it transmits that instant light signal into digital signal. So I also not spent any time on the photodetector because we talked about it in our previous lecture. Okay, so again, so you are going to build it differently. So there are two LEDs. So you have to very closely space your LEDs and the photodetector to be able to accept the signal. In addition to these LEDs, we will have a room light, illumination light, which flickers at 60 hertz. Okay, so the signal, the output signal will be very noisy. So, by adding this filter, actually a high pass filter, you only select high frequency signal. Okay, so let's talk about signal resistance a little bit now. Okay. So you already took a signal resistance, right? Signal resistance, right? You already took a class. No, signal resistance. 실험이 시스템은 들었어요? 저 엄청 옛날에 엄청 들었어요. 한번 들었네요. Okay, so let's try to model this. Let's try to model the whole system. Okay. So yeah, we have to have some model to analyze or to characterize the system. So that's what we learned during the signal system. So we apply what we've learned in this system. So let's start from the signal from the board. Okay? So you generate the signal. And you may model that signal with A1 times cosine omega 1t plus phi 1. It might be a series of harmonics because we are actually generating square waves. Okay? So you already learned how to describe the square wave in terms of the sum of the harmonics. But it will have that kind of compounds. Okay? And the low frequency signal, there are two signals, right? High frequency and low frequencies. And the low frequency signal will have a different form. Okay? It has different frequencies, omega 1 and omega 2. So that will be the output from the board. And my question will be, how can you model the right output from the LED? Will it be proportional to each other? Or what do you think? Yeah, what do you think?
Add.
Huh?
Add the two signals.
Add the two signals? Maybe not, because let's think about this one more time. Yeah, if you let's say you generate like a 10 megahertz signal at the board. Will you observe 10 megahertz signal at the right output? Maybe not, because the LEDs have their own frequencies, right? And we also have this resistors and capacitors. So the output from this LED might not exactly follow the voltage output. Okay? So you have signal, the input signal. And this LED may have its own transfer function. It might not be a linear system. It might not be an LTI system, but we can assume that. We can safely assume that here. We can safely assume that this is actually an LTI system. If it is an LTI system, or actually the whole process, the conversion of the voltage signal to the right can be considered as an LTI system. Maybe it's a low pass filter LTI system. So it has some transfer function. And the output of this filter will be, well, it will represent the right output. Okay? And we have two inputs, input 1 and input 2. So it will generate two signals, and they will be added. You generate two signals independently, and if you just look at them, then you will see both of them flickering together with different frequencies. And up to here, at this point, it will be something like this. It might be different from this one, but it may have this kind of form. And after passing through some free space air, it will hit this photo detector. Okay? And the photo current, or the output voltage at this point. There's another transfer function. There's another transfer function. So what was the bandwidth of the photo detector or photo transistor? So you have characterized that, characteristics this way, right? So that was the main things you need to find from the results of this week's experiment. You need to understand those things to design your system, communication systems for next week. So what's the photocurrent signal from the photo detector in your receiver circuit? You can model them. So we know that the photocurrent is proportional to the incoming light intensity, right? R times P is, we talked about responsivity and other concepts last week. So I'm pretty sure you can find that the output signal. You need to consider the register variable and everything. Anyway. So from here, you can do many things. But at this point, let's try to think about the frequency components at this point. So either have high frequency components. You can have some high frequency components, and you can also have some low frequency components. And it may have some noise. So at this point, if you measure the signal, here, then you have everything. Okay? High frequency signal, low frequency signal, and some noise. Noise might be coming from the room illumination or some light from the sun. I don't know. There can be many sources. If you turn on your mobile devices, then it also generates light. There are many sources that you can disturb the output signal at here. But as I mentioned earlier, the main goal of next week's experiment is to filter out everything and to recover this signal. How do you do it? Or if you want to recover only the low frequency signal, then what should we do? The answer is here. The answer is we can use the filter. And I'm pretty sure you have learned about the filter before. How about you? Filter, yeah. Filter. So, I'm glad to hear that you learned about the filter before. Okay, so far, so good. And if we apply a filter, and if it is especially high-pass filter, then we may extract this high frequency signal. But think about other things. Is it really an LTI system? If it is not an LTI system, then we cannot use this kind of a modeling. What happens if the system is non-linear? It might not be non-linear. It might be non-linear. So in this week's experiment, in experiment 6, you measure the IV characteristics and the small signal resistance and that kind of thing. And they are not quite linear, especially when your input signal varies a lot. When it changes within a small amplitude, then you may consider it a linear, but if it changes from 0 volt to 5 volt, you might not be able to assume that it's a linear. Maybe, maybe not. If you think about it. Okay, so anyway, we are going to use a high-pass filter to filter out only the high-frequency signal among many signals, among many users. And luckily, you already learned about this kind of thing before, so I'm not going to spend a lot of time to describe the filter. And but what I would like to emphasize here is that you are going to use active filter. You are going to use this OPM, operational amplifier, to design amplifying high-pass filter. You are not just discriminating a low frequency, but you also amplifying at the same time, because the photo currents might be small. But there are many kinds of filters, and especially here in this slide, this is a first order filter. And of course you can design a second order filter by adding one more capacitor. 이게 왜 하이패스 필터가 되는지 알죠? 설명 안 해도 되겠죠? 네, 질문하시면 돼요. 이거 왜 하이패스 필터 되는지는 알죠? 설명 시간에 나오나요? 설명 배우지 않았더라도 저걸 해석을 하면 하이패스가 되는 건 알 수 있겠죠?
절도 안 하셨다.
그러니까 어디서 절반하는 거예요?
C 쪽 커패시턴스에서
절과 아들은 여기하고 여기 사이에 아들은 거죠. 여기 사이에 뭐 흐를 수도 있죠.
이제 프리퀀시가 낮으면 흐를 수 있나요?
아, 네, 그렇죠. 프리퀀시가 낮으면 잘 안 나죠.
그때 우리가 하이패스.
네. 다른 사람도 이해했어요? So even if you didn't learn about the detailed geometry, the specific geometry shown here, I think you can analyze this kind of thing by the theories you have learned in circuit theory. And this thing as well. So it has two capacitors, 1 over j omega c. So there are two 1 over j omega c. So it has 2 poles with a faster roll-off. And why do we need higher order filter? Why do we need higher order filter? So we have to discriminate the high frequency signal and low frequency signal, and they have the frequency difference, high frequency signal and low frequency signal. And we want to delete the low frequency signal. To do that, the gain at this frequency must be low enough compared to the high frequency. If this roll-off is very slow, then you might not give a big discrimination between the high frequency signal and low frequency signal. The gain between the high frequency and low frequency should be large enough. Okay. So to be able to do so, you have to have very steep roll-off. You need a big discrepancy, a big change between the pass band and the stop band to completely kill this concept. If you don't do so, if you don't completely kill this line, then what we will measure after the high-pass filter will still be the combination of low frequency signals and high frequency signals. So it will be very noisy. Okay. So you need to design your filter wisely so that you can completely suppress the low frequency signals. And that's your job for the pre-lab report. You need to design your filter so that you can directly start to plug your components in the lab to finish your experiments as early as possible. Okay, so this is the additional thing. So there's some relationship between the low pass filter and high pass filter. So if you just change the RAC, then you can convert the low and high frequency signals. Okay, before finishing, let me go over the experiment guide. Okay, so this is the English version. So the objective, problem statement, the background. And the background explains the way to generate the pulses. And this is basically saying that what I explained today. And so forth. So let's talk about this pre-lab report. Okay, first part A. Study the functions of registers related to the timer and counter in Arduino 128, including TIMSK and TCCR. So TIMSK and TCCR sets the properties of the counter and timer. So if you set it widely, then you can control the output frequency. Okay, so that's something you need to do. So that's the hint. Okay, part B. Explain a method to generate high and low frequency signal. So high frequency signal should be larger than 200 Hz, but below 5 kHz. It's set 200 Hz because you are going to make a high pass filter with a cutoff frequency of 200 Hz. So high frequency signal should be larger than the cutoff frequency of the high pass filter, and the low frequency signal should be smaller than 20 Hz. So make your choice. Make your choice. But in the end, you need to have very good signal suppression for the low frequency signal. Okay? So if you set high frequency at 201 Hz and if you set the low frequency at 199, then it will be very difficult for your filter to discriminate between those two signals. So think wisely. Okay? Set your frequency. And after setting your frequency, you have to find a way to generate that frequency using your Arduino 128. Okay? Using prescaler and timer counter. Okay? And you need to include your own program code. If you have your code, then you can just download that code in the lab just to directly generate your frequency signal. And I'm pretty sure you have done that kind of thing in the previous labs. 계산기 시간을 해봤죠? 네. 프로그램 다운로드해서 실행하는 거 똑같이 하면 되죠. Okay, part C. Part C. 그래서 그 프로그램이 다들 있어요? AV, RAP 있어요? 컴퓨터 빨리 있어요? 컴퓨터? Okay, part C. Investigate the active and passive filters. Okay, so that's about the filters. Okay, so design a filter. So part D, design a high pass filter, considering various aspects such as the filter performance, number of amplifiers, and the filter observability. What you have to have in your mind is to make a maximum difference between your low frequency signal and high frequency signal. Of course, you can make good filters by cascading many filters. So we will give up to 3 operational amplifiers. You have up to 3, not 10, not 100, not 1, but you can use 1, 2, or 3 operational amplifiers, and you have a freedom of designing your own high-pass filter within that limit. So if you finish your design, then you can just start plugging in those filters at the lab session to shorten your lab time. Okay, so experiments. The first experiment will characterize your high-pass filter design. So you design your filter in the pre-lab report, and then you measure the Bode plot of your filter. Okay, so your results, experiment results, might or might not follow your theoretical prediction. So this is basically to draw the Bode plot by measuring the gain. So when you fill up this table, and if you just plot it on a graph, then you can measure the 3 dB bandwidths and so forth. And the second part, you will be generating 2 signals, two frequency signals, low frequency and high frequency. Again, if you have finished your code, then it will be faster. So the hints is the TIMSK and TCCR. And the final part of the experiment is to connect those two. Okay, so the high-pass filter part is about the receiver side, and in part 2 you have just finished the transmitter part, and in the last part you connect them. Just place your detector close to your LEDs, and then to see whether your filter works or not. So this is a part 1, this is part 2, and part 3 includes everything. So your lab time might be shorter than the spec, but if you include everything, like a pre-lab reports, then it might be longer. So, and it's actually quite important. You finish your filter design and the frequency generation code before you come to the lab. Okay, any questions?
LED를 2개 쓰는데 포토 트랜지스터 하나만
쓰요.
이거
두 개가 이렇게 있고 하나가 이렇게 있어요.
근데 딱 안 맞추면 잘 안 되죠.
그래서 뭐 트릭을 쓸 수도 있고, 하이 프리퀀시 쪽에 더 가까이 있고, 뭐 이거 조율 맞고. 두 개 다 이제 가운데 쭉. Any questions?
네. 실험할 때 데모 순서되는데 너무 오래 기다리는데
그거를 좀 개선을 하도록 하겠습니다. 이게 이제 뭐 질문이 첫 번째 질문 좀 많았을 수도 있는데 그걸 좀 줄인다든지 해서 조절이랑 한번 논의를 해보죠. 이번에는 지난번 실험 5나 4 이런 거에 비해서 그 질문 시간이 더 길었어요. 그래서 더 길어진 거예요.
많이 기다리잖아요.
그 전에는 이런 일이 없었어요. 질문 전에는.
그렇게 심하진 않아.
그러니까 그게 이유가 그 질문이 짧았기 때문에 그런 거예요.
그런 것도 있고 방법이 아예 달라요. 시작할 때 퀴즈로
시작할 때. 매번 그렇기 때문에 맨 처음에 어떻게 될지 잘 몰라요. 사람들이 이제 또 처음 해보는 실험이니까 뭐 4시간이 걸릴지 8시간이 걸릴지 잘 모르는 상태에서 시험을 하다 보니까